Discussion of lipids. Okay. Is everything we're covering today on the test on Thursday? Yes, it is. Okay. Um, so yeah, that was a private message question. Is this basically is the stuff that we're covering today on Thursday's test? Yes, it is. Okay. Now, lipids. Lipids are substances of biological origin that are soluble in organic solvents. They are soluble in organic solvents, not in inorganic. Now, the most important things about lipids are that, like, what roles do they play? Lipids form a bilayer that are essential components of membranes. So if you've ever heard the phrase lipid bilayer, well, then we're about to learn about the thing that is absolutely vital for that. Lipids contain hydrocarbon side chains as energy stores. So lipids are robust sources of energy. Now, many intra and intercellular signaling events involve lipid molecules. Lipids are classified in 5 different ways, but before I get to that, I just want to highlight this. Okay, so what are the roles of lipids? Protection, energy, and communication. So anytime that we're talking about a lipid, I want you to be trying to put whatever that lipid is into one of these 3 frames, into these 3 buckets. Is this a lipid that's going to play a role in protection? Is it an energy source, or is it going to be used for communication? Now, your classes of lipids. Personally, I always think about fatty acids, and I unfortunately have the bad habit of using the term lipid as synonymous with fatty acids and triacylglycerols, that and glycerophospholipids. We are starting with fatty acids. Now, when you think about a fatty acid, I want you to think about, well, first of all, an acid and an alkyl chain. Now, when you think about an acid, I want you to think about a carboxylic acid or a carboxyl group. And an alkyl chain, hydrocarbons, or a hydrocarbon tail. Now, which one of these do you think is polar? The carboxyl group or the hydrocarbon tail? One for carboxyl group, 2 for hydrocarbon tail. Add it to the chat. Absolutely. You've got a carboxyl group. Well, a carboxylate ion, negatively charged. Your hydrocarbon chain, very nonpolar. Now, when we look at fatty acids, here are 4 examples of fatty acids. Is there a difference between them? Yes, there is. We've got a double bond, 2 double bonds, or 1, 2, 3 double bonds. Now, what is significant about that is that changes the properties of these 3 fatty acids, or these 4 fatty acids. They're all 18 carbons long, but some of them have double bonds, some of them don't. Now, if you relate any of this to any sort of dietary or nutrition advice or nutritional information that you have, I think that's a good place to start. I think that's a good piece of information and good context to use. Now, fatty acids are carboxylic acids up at the top here with long hydrocarbon side groups. Now, predominant fatty acids in plants and animals are 16 and 18 carbons long. This notation, C16, is common. C20, C24. I'm just using this number to indicate, well, something you might want to see. If you were to see a fatty acid is described as C20, how many carbons do you think that it has? Add it to the chat. Absolutely, 20 carbons. Now, the difference between these 4 fatty acids is that they are saturated or unsaturated. Now, the way that I think about this, and I hope that this is helpful, is whenever I look at this molecule right here, this is known as stearic acid. I'm not going to ask you to know specific names of fatty acids, but whenever you look at this molecule, I want you to think that, oh, looking at this hydrocarbon chain. Can you put any other hydrogens on there? Y or N to the chat. Is there any place that you can add a hydrogen? No. I always try to think about these as they are saturated with hydrogens. They cannot take on any others. Now, if we look at those fatty acids, those fatty acid tails with double bonds, are there places that you could put a hydrogen? If you look at this right here. Yeah, absolutely. There's a double bond. You could add two hydrogens there and you sacrifice the double bond there. These are unsaturated, and these two specifically are poly unsaturated. If you've ever heard um, dietary advice that says increase the number of PUFAs, polyunsaturated fatty acids. These, linoleic and alpha linolenic acid, are both examples of polyunsaturated fatty acids because they have more than one double bond. Now, one thing that I want to bring back is if you look at the top, oh, those all have double bonds. Well, when they are carboxylate ions, they don't. We don't look at this double bond and count that as a part of, oh, is it saturated or unsaturated? When it comes to saturation or unsaturation or polyunsaturation, we are just looking at does the alkyl chain have double bonds? Now, when we go on from there, this next level of nomenclature, C18, how many carbons does this fatty acid have? Add it to the chat. 18 carbons, perfect. Now, what I want you to be comfortable with is C18 colon and then a number. What do you think that this 2 means right here with C18 colon 2? Hmm. Double bonds, perfect. The number of double bonds. So if we saw C18 colon 2, that is in reference to linoleic acid. C18 colon 3 would be alpha linolenic acid. Okay. Now, I'm sure that you're probably thinking, yeah, but what about the positioning of those double bonds? Does that matter? It does. And we're going to get to that in just a moment. But before we do, I want you to know a couple of things. One is that all double bonds, naturally occurring fatty acids, are in the cis configuration as opposed to the trans configuration. We will get to double bond location in just a little bit, but this number that follows the colon, that just indicates the number of double bonds. Now, the first double bond is typically between carbons number 9 and 10. So here, what we have with oleic, linoleic, and alpha linolenic fatty acids or acid, we have that double bond between carbons number 9 and 10. Now, these are simply examples of fatty acids. Polyunsaturated fatty acids, one thing that's important to recognize about those, and the way that I think is helpful to think about it and visualize this is, well, one, you need to know that they are not conjugated. But the way that is helpful for me to think about it is to visualize a fatty acid and say, okay, our naturally occurring fatty acids will have a pattern of D for double, S for single, S for single, D for double. So when I see this and I'm just envisioning like, okay, where are my double bonds? The pattern is going to be, if it is a polyunsaturated fatty acid, will be D, so a double bond followed by a single, followed by a single, followed by a double, followed by a single, followed by a single, followed by a double, followed by a single, followed by a single, followed by a double. This would be an example of a polyunsaturated fatty acid, and this would be colon 4 to indicate the number. Now, with that in mind, thinking about cis fatty acids or trans fats, well, I'm talking about the naturally occurring fatty acids, and the positioning of double bonds can vary. Just as it's not always going to be between carbons number 9 and 10, it usually is. Okay, now just to plant a little bit of a seed here. Oh, so give me a Y if you follow this pattern and understand what this means, or an N if no, I didn't hear that. Okay. So we've got a double bond between carbons number 9 and 10 in all of these fatty acids. Double bonds don't always start there, but this carbon number 9 right here, that numbering is based on our carboxyl carbon. Okay, so this is carbon number 1, this is carbon number 9, this is carbon number 18. Could you give me a emoji in the chat if you understand that numbering? Okay. Now, I'm going to jump ahead a couple of slides in this slide deck to address or to bring that point up and bring that point back. Here's those same four fatty acids. Can everyone give me, yeah, okay. I'm not going to ask you because we all did emojis. Good job. Thank you very much. So we've got these four fatty acids. There are two different ways of communicating where a double bond is in a fatty acid. Could you give me a Y if you've ever heard of omega fatty acids? Okay. Now, what these four fatty acids, stearic acid, you would denote as C18 colon 0 because there are no double bonds in it. Oleic acid, C18 colon 1. Then the last thing that you're going to add to kind of visualize that completely is to say delta 9. Linoleic acid, C18 colon 1, delta 9. And sometimes you'd see delta 9 comma 12, or maybe you'd see delta 9 delta 12. But that delta, that's indicating where our double bond begins. So starting at carbon number 9, starting at carbon number 12. And then for this last fatty acid over here, could everyone add, and you can use a lowercase d to indicate the delta. What is the kind of description or configuration of this? Okay, so I got C18 colon 3, D9, 12, and 15. Why doesn't it start at the carbonyl? It does in this case. This is our delta numbering scheme that follows the starting at carbon number 1. So C18 colon 3, delta 9, 12, and 15. Now, that is one way in which fatty acids are described. Great question. Why couldn't you just write C18 colon 3? Because, like I said, fatty acids are not always going to start at position number 9. Isn't the third one supposed to be 18 colon 2? No, because the third one has 1, 2, 3 double bonds at carbon number 9, 12, and 15. Great question. Okay, so okay, that is a great question because that is actually what we reference with our other nomenclature system. Okay, I mean linoleic acid. Well, oh, sorry, 18 colon 2. I got ahead of myself. I wrote 18 colon 1. Thank you very much for bringing that up, Asma. Okay, so so this numbering scheme, I always kind of look at this, and Melanie, you've got such a you're on top of it completely. I look at this delta scheme as being explicit. It tells you exactly where every double bond is. Now, in contrast to that, we have the omega numbering system and the omega numbering scheme. That is this, the omega or N numbering scheme. In this case, if you have a double bond or if you have a polyunsaturated fatty acid, you do not indicate where each one is. So in this case, you would say, all right, well, so actually, let me add up a couple of details. With the omega numbering scheme, you do not note where each, I'm going to change that to specify. You do not specify. You don't specify where each DB or double bond is. Okay. Another thing is you don't start at the carboxyl group. Oh, huh. What's the omega? Typically, what does that mean? Well, sometimes it's used to mean end or terminal. So we're not starting with the carbonyl group or the carboxyl group. Instead, we're talking about the methyl end. So the numbering for the omega fatty acids doesn't start with the carboxyl group. So when you see like this molecule right here, this is an omega-3 fatty acid. If you look at the total number of carbons, one, two, three, four, five, and then N, so that could be any number of them, and then this. So we could be talking about C18 colon 1, N minus 3. In order for this to be 18, this N would have to be 12. Okay. So the biggest details that are important for the omega fatty acids is you don't specify where each double bond is. You're operating under the idea of, oh, well, we have this pattern. That pattern is the double bonds are not conjugated. So we've got a DSSB. So with that in mind, DSSD, not B, if we jump ahead a little bit, try using for alpha linolenic acid, C18 colon 3. Now label this with the omega or N numbering scheme. And add it to the chat. N minus 3, because carbon 1, 2, 3. It's all about kind of the perspective. And this omega system it is not as explicit, but it's kind of like a gatekeeper almost of knowledge. It's like, well, 18 colon 3, you know that these double bonds are not conjugated. So you know that the first double bond begins here. And then it's going to be a single bond, double bond, single bond, double bond. Can you give me a 1 in the chat if you understand that in application to alpha linolenic acid? Okay, so then if we look at linoleic acid, well, C18 colon 2, N minus 1, 2, 3, 4, 5, 6. That's all that you need to provide for that. Now, oleic acid, well, C18 colon 1, N minus 1, 2, 3, 4, 5, 6, 7, 8, 9. N minus 9. Now that's a little bit confusing because this delta, when you look at the delta and the omega numbering, it's like, oh, well, they're the same. That's just kind of a coincidence due to the length of this fatty acid's alkyl chain. Okay, so could you give me a 1 if you feel good about, so you don't need to include the other double bonds, just the first. For the omega system, yes. For the delta system, no. Delta is more detailed. I always think of delta detail. And if I started a car detailing business, that's what it would be called, delta detail. Okay, so give me a 1 if you feel good about distinguishing these two things and interpreting this notation, or a U if it's confusing. Okay. So the important thing is to think about where are you starting from? Omega, your numbering starts with the methyl. And delta, delta starts with the carboxyl group. All right. So that's what you need to keep straight from one another. Where does your numbering begin and what do you include? Now, with that in mind, fatty acids. Your saturated fatty acids are going to pack really tightly together, which is one reason that people say, oh, you should eat lots of polyunsaturated fatty acids. The reason is because those fats don't pack very well together. So, saturated fatty acids versus polyunsaturated fatty acids. Saturated fatty acids, if you eat a small amount, you're going to get a lot of energy from them. So, thinking about this in the context of energy as opposed to communication or protection. So saturated fatty acids pack super tightly. So if they've just got, or if they have no double bonds, then they're going to be super dense. That's like bacon grease, bacon fat. Now, your unsaturated fatty acids, they have kind of this kink, and they have this kind of like curve, in which case unsaturated fatty acids pack in a less ordered way. And we see that down here at the bottom. Your saturated fatty acids, in this space, you get five of them packed together. And in that same approximate space, you get four or three. A smaller number of fatty acids are able to pack as well in that same space. Now, fatty acids, in terms of their melting points and properties related to, or physical properties, here what we have is a list of saturated fatty acids. Their melting points. What do you notice about those melting points? As the numbers of carbons increase, 12, 14, 16, 18, 20 carbons, what does their melting point do? 12 carbons has a melting point of 44 or 40, yeah, 44. 24 carbons, our melting point is up to 86 degrees. So, okay, as our number of carbons increases, our melting point increases. Okay. Now, if we look at the bottom down here, I'm going to pick out a couple. I'm going to pick out these three right here. And I want to compare those to this one right here. Our 18 carbon octadecanoic acid, also known as stearic acid, when it is completely saturated, has a melting point of 69.6 degrees Celsius. Okay. Now, if you add a single double bond in there, so if you add one double bond, what happens to your melting point? It drops all the way down to 13.4 degrees Celsius. So I always like to think about this in terms of like cooking almost. C18 colon 0 at room temperature, RT. Is that going to be a solid, a liquid, or a gas? Well, at room temperature, C18 colon 0, that is absolutely a solid. If our temperature is, 23, 25 degrees Celsius, that is absolutely a solid. Oh, but then when we have 18 colon 1, what happens? Are we a solid still? Nope, it's a liquid. And that's a drop of like 50 degrees. When we introduce a second double bond, 18 colon 2, 9, 12. Our melting point drops anywhere between, or sorry, it drops to a range of between 1 and 5 degrees Celsius. So 18 colon 2, well, that's also going to be a liquid at room temperature. 18 colon 3, 9, 12, and 15, our melting point drops all the way to negative 11. So we are absolutely going to have a liquid at room temperature. Okay, so a takeaway from this is as you increase the number of carbons, your melting temperature is going to go up. As you increase the number of double bonds, that's going to cause your melting temperature to go down. And what's arguably more important with that is, well, your melting temperature is going to, be more influenced by the number of double bonds. Okay, now this has a connection to energy because if it takes more energy for something to convert from a solid to, if it takes more energy, if the melting point is higher, it's going to take more energy for that thing to undergo a phase change. So give me a 1 if you feel good about this detail, and a 3 if, wait, I can't keep that straight. Great. Okay. So this is kind of your our nuts and bolts of fatty acids. We've got a polar head group, a non-polar side chain coming off of it. The larger the molecule is, the higher the melting temperature, but the greater number of double bonds, then the lower the melting temperature. I need you to keep straight the delta and the N or omega numbering scheme. Understand where you're starting your numbering from, and that's just all those displayed. Now, these are ultimately going to be integrated as a part of a triacylglycerol, or also known as a triglyceride. So, if we go back to one of our earlier slides, we talked about classification. Fatty acids, we're done with that. Now we're going on to triacylglycerols. So, our triacylglycerols are basically the closest thing that we have to a fatty acid or a lipid polymer. We've talked about sugars that form polymers. We've talked about amino acids that form polymers. Triglycerols or triacylglycerols or triglycerides, these are not polymers. They're larger molecules, but it's not like these can go on and repeat indefinitely or repeat for forever. The backbone of a triacylglycerol is a glycerol molecule. Then these get acylated. And what I mean by that is that OH group is replaced by a carboxyl group. Oh, and then we've got this alkyl chain coming off of it. So this group, this polar head group, or this polar end of a fatty acid, is what ultimately helps this hydroxyl group get booted off. So this is an example of a triacylglycerol, and this is a more detailed example of a triacylglycerol or triglyceride, where we have fatty acid tails of different chains. A triglycerol or a triglyceride is a fatty acid triester of glycerol. Most of these are going to contain 2 or 3 different types of fatty acid residues. So when you have a triglyceride, you're going to have groups here, here, and here that are different from one another. Now, the melting temperature of fatty acids. We already talked about this with respect to individual fatty acids, but if you think about fats that you consume, animal fats like bacon fat or butter, um, or yeah, bacon fat or I don't know, gristle in like a steak or something like that. That's a high percentage of saturated fatty acid residues. Plant fats, also known for fun as phytofats, well, they have a high percentage of unsaturated fatty acids. So if we look at olive oil, for example, well, olive oil, the vast majority of olive oil is 16 to 18 carbon long unsaturated fatty acids. Beef fat compared to olive oil and butter, well, beef fat has a lot of 16 and 18 carbon long saturated fatty acids. So all of these different fats are mixtures of different things. Now, in terms of triacylglycerols, they function as energy reservoirs in animals. The fat content of normal humans allows them to survive starvation for 2 or 3 months. So, fat stores that people have on their bodies, well, they can have a lot of energy reserved. Now, there's every time I forget his name, there's a guy that I always like to bring up, and his last name, there's a guy back in the 1970s who, under medical supervision, he basically fasted for an entire year. I think it was his fast was like 367 days or something like that. 367, I got it. 367-day fast. Um, Agnes Barbieri. Angus, not Agnes. I'm going to add this to the chat. Um, and I always like to bring this up to illustrate the energy value that fats have. Um, so this guy fasted for, what was it? From the 14th of June, 382 days. From the 14th of June, 1965 to the 30th of June, 1966. And well, yeah, he went from 456 pounds to 180 pounds. And he did not eat. So there we go. It was just like he drank electrolyte solutions and had vitamins, and there was enough energy stored in his body to basically keep that going. Now, triacylglycerols. So triacylglycerols or triglycerides primarily function to insulate. Um, the process by which fats are broken down. Has anyone ever seen the movie or read the book Fight Club? If you have, add F to the chat. Well, in that book, one of the things that they do is they go through this process of saponification. They get fats from in the movie, yeah, it was from liposuctions, and they use sodium hydroxide or a strong base to make soap. If you've ever been to Cincinnati, Ohio, or the Nasty Natty, as it's commonly called, among my friend Doug who lives there, um, that city is really built on Procter and Gamble, which Procter and Gamble, one of the things that they, yeah, I did. You're right. Shame, shame. Procter and Gamble, among the everything that they make, one of the things that they made was soap. And so there's lots of pig statues everywhere because, well, they would render fat from pigs to make soap. Um, so this is an industrial process, and in Fight Club, that's what they did. They use saponification to break down fats. Now, in our bodies, we use enzymes known as lipases to break those down. So they take a triacylglycerol and they break it into individual fatty acids, ionized fatty acids, as opposed to a sodium salt of fatty acid. Saponification is that process. I want you to know that. Now, olestra is something that I bring up. It's a fat substitute that has really kind of gone to be unpopular. And I don't even think that it's in anything now. In the mid 90s, it was like, oh, you can eat fat-free Doritos. And Olestra was the fat supplement or the fat alternative. And so basically, what it consisted of was you had something that looked like a ring. It was a carbohydrate fat substitute. So all these OH groups were replaced by um, uh, I'm just going to draw alkyl chains. So you had these molecules that looked like a carbohydrate, but also looked like a fat. And it was like, oh, this is great. You can make fat-rich foods, but your body gets it. And they're like, I don't know what to do with this. Well, I guess just get rid of it. And that was a really great idea. But then um, if you've ever heard of Wow brand chips, wow. Frito-Lay, I think, developed Olestra, and you'd get the chips, and it was like, oh, great, I'm eating Doritos, and my body's not getting any of this fat. And then everyone would have very violent and unpleasant GI issues. And then, as it turns out, people were like, you know what? I don't think I like Doritos that much. And then Frito-Lay was like, ooh, let's take this off the shelf. At any rate, okay, so what we've talked about so far is individual fatty acids and the physical properties, the nomenclature of individual fatty acids. Now we're talking about triacylglycerols, where, okay, so this is our molecule that what it's primarily doing is it's providing some insulation, so it's kind of a part of a membrane, but it's also an energy reservoir. So a triacylglycerol is great because it holds on to three fatty acids. Now, fats and lipids can be classified in two different ways. They can be classified as polar or a non-polar lipid. Triacylglycerol, for example, is an example of a non-polar lipid. A glycerophospholipid and sphingomyelins are examples of polar lipids. Now, to take those for just a moment, your non-polar lipids are going to be your energy storage, whereas your polar lipids, your glycerophospholipids, And derivatives of those, for example, sphingomyelins, are examples or the major building blocks of your lipid bilayers. So, what my aim is to, before the end of class, is to get to a point where we talk about, okay, we're going to arrive at here's what a lipid bilayer consists of. Now, glycerophospholipids. These are major lipid components of your biological membranes. If you've ever talked about a lipid bilayer or a membrane, you probably talked about a polar head group and a non-polar tail. Now, previously I talked about a carboxyl group or carboxyl group being polar. It is. But when we talk about as a part of a lipid bilayer, let's take this glycerophospholipid for an example. A glycerophospholipid is an amphiphilic molecule. What that means is that it has a polar region and a nonpolar region. In addition to that, the polar region is not coming from the carboxyl group, but instead from a phosphoryl X head group. Okay, so in order to construct a glycerophospholipid, you have a molecule like this, glycerol 3-phosphate. And to that, you add a fatty acid and another fatty acid. This phosphate group here is then targeted for modification and the addition of something to it. Okay, so if we look at this glycerophospholipid, we have the glycero or the glycerol backbone. We have a phosphate group. And then we have two, I'm going to change my color on those, are two fatty acid chains. Here's one, and here's the other. So if you think about a glycerophospholipid, you have a pair of fatty acid chains and a phosphoryl head group. That phosphoryl head group is going to be modified. Now, I'm going to switch to the next slide where we see, again, I'm going to highlight the glycerol backbone. There's our glycerol backbone. Then here is one fatty acid. Here's another fatty acid. After that, we have our phosphate group. Okay, so all of this makes a glycerophospholipid. So glycerol phospholipid. The phosphate group that I've highlighted or circled in black or put a square around in black, that can be modified. And the place or the position that that's modified is this X. That X gets replaced or is the place where any number of things can be added to it. These are some of those things that can be added to it. Now, you might think, oh, okay, cool, neat. This is a part of these are parts of like a part of a membrane. Got it. Cool. Okay. Um, the things in red, how would you classify those? Polar or non-polar? Specifically, I'm thinking about these R groups. Polar or non-polar? Those R groups are, yeah, non-polar. Those R groups are our alkyl chains. Okay. Then how would you classify this phosphate group here? Polar or non-polar? Polar. Great. Okay. So the way that I always kind of think about this is, and I'm going to redraw it. Here's my glycerol backbone. And I'm going to do kind of a rough model of it. There's my phosphate. I'm going to say R1 and then R2. Does everyone follow that remodeling there? Can you give me a 1 if, okay, I see how things are reconfigured, and a 5 if I don't follow. Okay. Now, which one of these is going to be embedded within the lipid bilayer? Is it going to be the R groups or the phosphate? R for R groups or P for phosphate? Thinking about like a lipid bilayer kind of looks like this. This region in here that I'm probably shouldn't scribble it with the identical colors that I've highlighted in yellow. What do we know about that region? Does a lot of water hang out in there? No. This region right here that I've highlighted in yellow, that is super hydrophobic. Can you give me a 5 if you follow that? Okay, asthma. Absolutely. These R groups are going to be in that hydrophobic region. So then the phosphate here, it's probably going to be out here. Now, this phosphate, like I said, that phosphate could, that little X on that phosphate, I'm going to go ahead and change colors to illustrate this. You could put this on here. So that X is going to be replaced by CH2, CH2, N. And I'm going to go ahead and draw all of these out. H, H, H plus. So that's protruding out. Could you give me an 8 in the chat if you follow that? And then any other character if you're confused. Okay. So that would be an example of an ethanolamine. Okay, cool. That would make the molecule phosphatidyl Now, just thinking about attraction. I think everyone would agree that this group is positively charged, the one that I just drew the red arrow to. So what do you think that positively charged group is going to do? What do you think it will attract? I think it's ions. Absolutely. It will attract negatively charged groups, negatively charged anions. Okay. So this is something that's protruding outward. What if we had a cell, or if there was another cell nearby that had, oh, that had this protruding outward? It has another glycerophospholipid, and this group is out. Well, that's negatively charged right there. Do you think that these two groups could come in contact with one another? Absolutely. Sorry, yes, they could. That negatively charged group is going to be a mechanism for communication. So when you think about glycerophospholipids, and actually before I proceed, could you give me a T if you follow that this is our mechanism for communication, or this is a means in which communication takes place between cells? And then any other character if you don't follow that. Okay, so the communication is kind of binary. It's like I have a positively charged group of a certain shape or size that is on my glycerophospholipid head group. That is displayed outward. Do you think that these groups can become much more complicated than two carbons and a nitrogen? Yes, they can become massive. For example, phosphatidylglycerol. This whole thing can find its place right here. Do you think that this molecule that I put a star by, do you think that's going to communicate from one cell the same thing that this group that I put a star by? Do you think they'll communicate the same thing? Y or N to the chat. And do you think that they'll communicate the same thing and attract the same things? No, not at all. This phosphatidylglycerol, making up this diphosphatidylglycerol, oh man, that's going to communicate. That's a big old bulky group with an extra phosphate. Ooh, this is going to be saying things that this phosphatidylethanolamin isn't capable of saying. So when you think about cell-to-cell communication, well, and cell-to-cell contacts, It's not necessarily mediated by contact between proteins. It's mediated by something as a part of a membrane connecting with something on another membrane. Because remember, human cells, do they have cell walls? No. They got a cell membrane. And that cell membrane with these glycerophospholipids, one, it maintains like structural integrity, but it's also a mechanism to communicate between each other. Okay. The next class of molecules is very similar to these. Now, in terms of which ones do I want you to know, I'm not really stressed about you guys knowing specific glycerophospholipids. I want you to know the structure of a glycerophospholipid. I want you to, if I showed it to you, you'd be able to say, oh, yeah, that's a glycerophospholipid, and identify it. These X head groups, this is just seven of them. There's almost, I don't know if I'd say there's an infinite number of them. There's a large number of these. And these molecules communicate different things. Now, another major part of lipid bilayers are sphingolipids, which is one of my favorite science words of all time. These are major membrane components. They are derivatives of the C18 amino alcohol sphingosine. Right here is sphingosine. C18. Here's one, here's 12 more, so that's 13, 14, 15, 16, 17, 18. Okay? This, to me, this right here, oh man, that looks a lot like that glycerol backbone. It's not, but it looks similar to it. Now, that amino alcohol, there's our amino group, and then we got some alcohols up here. That sphingosine, that amino group, can be modified to get a fatty acid onto it. And whenever it does, that is known as a ceramide. The basic unit of all sphingolipids is a ceramide. So the modified form of a sphingolipid has, well, the 18 carbons that make up the general backbone. Then a fatty acid added to the amino group. Then a head group. So this is again kind of that thing that's protruding out from a cell. Now, these are going to be kind of displayed out to other cells. In some circumstances, if we imagine this is our lipid bilayer, you might have, here's this X that represents that phosphocholine group, this head group. But then there are other instances where a cell is going to say, well, let's not display that. Instead, we need to communicate to other cells that we don't have that, or so we're going to flip that inward. Okay. All right. Now, the last thing that I want you to know about is the enzymes, the lipases that are responsible for processing glycerophospholipids. You have three different major phospholipases, A, C, and D. There's A1, A2, C, and D. A1 and A2, what they are capable of doing is they are capable of removing fatty acids. A1 and A2 remove FA, or fatty acids. The A1 corresponds to, well, on carbon number 1. And A2 corresponds to C number 2. Now, phospholipase C and D. Well, these will both C and D cut off polar head groups. Could anyone tell me what's the difference between C and D? Or let me rephrase that. Is there one of these phospholipases, C or D, that will cut off a phosphorylated head group and one that will cut off the non-phosphorylated head group? Which one of them will cut and release a phosphorylated head group? Well, what we have to look for is, here's our glycerol backbone. C is going to cut here. So this X, which is our head group, phospholipase C will cut and X will take the phosphate. Phospholipase D will just cut off the X. So both C and D will cut off the polar head group, but C leaves it phosphorylated, and D, it is not phosphorylated. Okay. Um, I'm going to stop right there. Oh, and cells are constantly taking this over and processing this over and over again. I'm going to send out some more updates regarding your exam or your Thursday exam later today. And I have office hours tomorrow at 11 a.m. If you want to hang around and ask me any questions right now, you're more than welcome to. Are you going to go? I am going to, thank you very much, Olivia. Are you going to post the test objectives? I thought that I already did, but I'm going to kind of cull the herd of that and make sure that the info that I've sent out, I'm going to give you a most up-to-date version of what you should expect. I'll do that later today. Um, but thanks for that. Thank you for that. If there's anything else, though, I'm here. Other than that, I'm going to stop the recording. I'll hang around for a little bit, and I hope that you guys have a great